Yeah, let me just stop this and erase.
Hi, Austin. I don't think Ryan needs a video.
Hi, Austin.
Already. Poor baby. He didn't get any review. That's bad, by the way, because it'll hurt your grade. Anyhow.
Here, you want to put it over here?
The things that you want to review, the lab final, the titration problem, there'll be a titration problem on the lab that's pretty much just like that. A monoprotic acid being titrated with a nice normal base. And there's another problem that is a diprotic acid.
Oh, what?
So like sulfuric acid is a diprotic acid. Phosphoric acid is a triprotic acid. So if you remember, hydrogen always forms the H plus ion, and then like the sulfate ion is a 2 minus, the phosphate ion is a 3 minus. So when you form sulfuric acid, you get H2SO4 because you cross their charges. Oh. When you get phosphoric acid, you get H3PO4. So when you have diprotic or triprotic acids, you cannot use the dilution equation to do the stoichiometry and figure out your titration math. You have to use stoichiometry. Module 10 covers all that, and you can review that. You'll have some of those on your quarterly exams that you're going to do before the final. So I'm not going to go over this problem. We had an extra session going over problems like this. During Module 10. Okay. So I know you guys know how to do it. You did the easy ones here in class just the other day. There's only one hard one.
The cameraman.
So
blurry.
Make sure that you review Module 10 math in particular. Make sure you know your polyatomic ions. Okay? Because when you write equations, you have to make every single compound right with their ions.
Oh wait, I might.
And you guys had experience with that in this station during the lab final.
So we have to know our polyatomic ions?
Polyatomic ions. Because remember when you wrote, like say you had magnesium hydroxide, right? Well, OH is a 1 minus, but magnesium is a 2 plus, right? So you have to do that. And then let's say you have lithium chloride. Well, lithium is a 1, chloride's a 1. So that's fine. But when you do the double replacement reaction, you get right? Because Mg is a 2, Cl is a 1.
Oh, not these stuff.
Right? So make sure that you know your polyatomic ions, and every time you write a balanced equation, you write each compound the way that compound needs to be. You don't just say, oh, well, I have 2 hydroxides there, so I'm going to have 2 there. No. You write the compound correctly based on how the ions form, and then you have to balance it. So here we balance thusly and be done with it. Right? So make sure you review that stuff.
Balancing equations.
Let's see. There's also at least one solution making problem, like that 5 molar sodium chloride solution you guys made in the lab final, where I'll tell you, say you're going to make it out of lithium chloride. Well, remember, when you're making a solution, you have to measure out your powder in grams, right?
So it's just like the one that we did in class?
Just like the one that you did in class, except that you'll find a molar mass of whatever thing you're making the solution of. And then you'll use the volume of the volumetric flask that you're going to fill. We used a 100 milliliter one, or a 0.1 liter. Maybe I'll give you a different size flask and a different compound, so a different molar mass, but it's the same thing. You know the concentration. In fact, I'm going to hand you your final right now, and I'm going to make you write something on the outside of it. So that it'll be
Oh, no, it's in an envelope. Okay.
Of course.
Oh, wait. Why does it have our names on it?
Just so I can't mess up.
Oh,
Or
I thought
y'all
it was like a certain test made for us.
I found the final on the floor, but I didn't know who dropped theirs last year. So at least now, if I, you can't
On.
mess up too bad.
So,
So we go. Wait a
what are
second.
we gonna write?
So what you're gonna write is capital M equals moles per liter.
We're allowed to use this on the test.
You need to make yourself a note card
Okay.
with
Like-
equations. This isn't exactly an equation. And
Number of moles, number of liters. I already have that.
That's like
Is
the
that a
smallest
one?
I've
Just to
ever
make.
seen
I'm
you
just making
write.
sure that's a one.
But then this one had like two equations, so I had to spread it
This
out
is
more.
moles per liter.
If you
moles
get stuck,
times, is it a 1 or
find-
a lowercase l? Up. Yes. Is that a 1?
if you
That.
Oh. I just want to make sure I was writing it right.
get stuck, find molar.
So take the periodic table. Add
So,
up.
what do we need? The periodic table and the polyatomic ion?
You may not have a chart of polyatomic
Oh.
ions. You need to memorize them. That's the fun of chemistry. But you may have a periodic table, and
What about that
you may have
other
your note
chart?
card and your
Okay.
calculator. So your note card may only have equations on it. It can't have words. It can have math equations. So things that you might want to consider.
No card.
You can't have chemical equations either. Just math equations.
What's the difference?
So you want to consider things
I
like
don't know. Like, which one's
a
that?
dilution equation.
Chemical equation.
Oh, well, duh. Do those all
The
work?
combined gas law.
Make sure we have these.
Oh yeah.
Okay.
Can we say which one is which? Like,
No, you have to know what it is. You have to know that's a dilution equation. You have to know that's combined gas law. And we'll talk about all these things in here. We'll keep moving. And I will actually keep a running tally of equations we use up there as we go through this. So you'll kind of have your sheets at least started. Okay, so take out your little sheet of stuff we're supposed to fill in. And also note that with this review sheet, the big thing is I'm probably going to go backwards. So if I ask you, how would you make your brother's soda go flat on this paper, then probably that means how would you cause gas to come out of solution in a liquid solution. I probably the final is going to ask you, how do you keep gas dissolved in a liquid, right? I mean, I give you things to review here. I'm probably going to give you something slightly different on the final. Is it still recording?
Yep.
Don't be distracted. Pay attention.
We're just checking to make sure they're all recorded.
I know the batteries will die. All right, so first question, why does the temperature of ice water stay 0.0 degrees Celsius even when energy is being added?
are you answering?
Yes. Nora, go ahead.
Because like all the energy is going to melting down.
Yes. As long as you're at a point where a phase change is occurring, and it doesn't have to be water, any phase change, anything, if copper's melting, if, ammonia that is a gas dissolved in a liquid
that's
is
the answer.
coming out of solution, whatever it's
energy's
doing.
melting
Anytime
ice.
you have a phase change, any energy that's being added to the system will go to causing the phase change. It will not go to increasing the temperature of the liquid. Conversely, since I'll usually use the opposite of the thing I ask on this sheet on the final, if you have something that is melting, the ice cube or whatever is melting will not change temperature until it's completely melted. Because all energy added to the system, or if it's freezing, say, you have water in the freezer, it's freezing, it will stay at 0 until it's frozen, then the frozen block of ice can continue to get colder.
So after the phase is completed.
Right,
That's
after
when-
it's solid, it can get colder. But while it's still freezing, if there's any tiny bit that is unfrozen, it will not get colder. But it can get colder after it's completely frozen. Exact same thing, why does the temperature of boiling water stay 100 degrees Celsius even if energy is being added? If the
All the
pot is
energy
raging on
is
the
going to heating it up, right?
Right. You can not get water hotter than 100 degrees Celsius because it is then giving energy to the molecules that are evaporating and becoming a gas. You can superheat steam to much hotter than 100 degrees Celsius, which if you've ever stuck your head in an oven you just opened and burned your eyeballs off, you will know. 250 degrees steam will shoot out of your oven if, you don't open like this, ever. Open like this and then lean over. I never did that until I moved into this house, and boiling like super hot steam comes rolling out of my oven for some reason. It's
Why?
awful. But it
That's
took me
weird.
2 times. You'd think you'd learn after the first time.
How does
How does calorimetry work, Dustin?
Oh, calorimetry. Crap, I forget.
You just said crap on film.
Oh, my bad. Oh well.
This is why it's so awkward for a teacher to film a class. Sorry, all of the moms who are listening. So, remember we had a calorimeter, right? It has a lid. It has something that is well
That's a lid.
insulated, like styrofoam.
How does it work?
Right? In our case, and this isn't the case, there are many kinds of calorimetry with different types of calorimeters, like the bomb calorimeter you'll use in college, where you pump it full of oxygen gas and blow up the contents. Great. Much more accurate. But ours actually worked really well. So you put in water, because water has a very high specific heat. See, remember? Because our calorimetry equation is what? Anyone remember calorimetry? Now, there won't be math. But the calorimetry equation is useful to have on your sheet because it'll remind you of the things that go on in a calorimetry experiment. Anyone remember?
Oh, it's the
Oh,
M delta T or M delta T or something.
Okay. So, calorimetry, the heat. Q is heat. So the heat, which we trap in the calorimeter with our well-insulated container, is going to be the mass times the
I do
specific
not have
heat, which
that
is
one.
C.
I don't think.
C is specific heat.
Maybe
Each
I should write it down.
compound, each element has a characteristic specific heat. You can identify a metal, particularly, in our case, using the specific heat of it, plus its density, plus its physical characteristics, right? So if you know its density is like 19 and its specific heat is like 0.3, then you're going to say, well, I have lead, right? And so this is one of the ways to identify an unknown metal. Dump it in some water, find its volume, find its mass, find its density. Then, and here density is mass times volume, right? Density is mass times volume. So then you do calorimetry, you find its
that one
specific heat, you can see that it's gray or copper colored or whatever. You can identify it almost always based on certain characteristics of it. Specific heat and density being the 2 best ones.
Oh, I need that one too.
So anyhow, you have your calorimeter, it's well insulated. In our case, we put water in it. You can put a variety of things in it to see the heat change. Then you get your metal or whatever you're doing your calorimetry on. We always did a chunk of metal, some pennies or a lump of lead or whatever. You get it hot. Now you know boiling water won't go above 100 degrees, but it'll be exactly 100 degrees, right? So you use boiling water to get it to a known temperature. Okay? If you soak that metal in boiling water for 5 or 10 minutes, you know it's going to be 100 degrees. Then you quickly put it in, put the lid on. Then you measure the heat change. Okay? Then you know the mass of the contents of the calorimeter, you know the specific heat of the water, and see, you could add up the 2 things in the calorimeter. You know the mass of the metal, you know the mass of the water, you know the specific heat of water, you want to know the specific heat of the metal, right? You know the temperature change, which is always the same. Like if the water was, well, find it. Let's say the water started out at 20 degrees Celsius and the metal started out at 100 degrees Celsius, and the whole thing finished at, let's say, 23 degrees Celsius. What's the heat change for the water, delta T?
Wait.
I'll give it a 0.0 just
Is it 100
so we have no
minus 23?
significant figure nightmare.
Mm,
What's the delta T? The change?
77.
It went from 20 degrees to 23 degrees.
Oh. 30. Yeah.
yeah.
I thought yours
3
was
degrees.
okay.
And how
Yeah,
about
me too.
metal to,
The oh, that would be 77.
Oh,
You were
okay.
right. But not yet.
okay,
Yeah.
so, here, obviously it lost heat, so it'll have a negative. So, then you can plug it all into that equation, and solve for the specific heat of the metal, and then you can identify the metal, or at least narrow it down to the few metals that have a specific heat close to that number. And then use density and other physical properties to identify the metal. That's the point of calorimetry. Bomb calorimeters in college are used to find calories in food, for example. That's how nutritionists get the information to put on labels for food, is they blow up some of that food, see how much temperature change you get, then they can tell how much energy was contained in that food, because Q is heat, that's energy, right?
So how do you write that as in wording? How does calorimetry work?
Well, I'm only asking you about this experiment. So you heat a metal to a known temperature, you put it into water of a known temperature, and then you measure the heat change. Then you can find the specific heat of the metal, or if you know what metal it is, then you can find the heat change of the system. So
Put the
you
metal
could,
in a water.
I would mention the equation in your thing, even though I will not require you to do a problem where you use that equation, because that is something that people always struggle with. You wrote a lab report on this, so I would recommend reading through it. Hope you did a good job.
And what was it? After you put it in the water, you do what?
Then you take its temperature. The heat, the metal and the water will come to a constant temperature at the end of the experiment, right? You just wait till the temperature stops changing, right? After a long time of measuring, they both the metal and the water ended up being 23 degrees. So once the temperature stops changing, then you can measure the temperature change for each object. So, number 3. So think this experiment was like in chapter 3 or 4. When we mixed vinegar and lye, mass was conserved. So I weighed a pile of lye on top of a beaker of vinegar, and then we mixed them, and we obviously had a chemical reaction, and then heat was given off. We saw a pH change because I put an indicator in there, but the mass didn't change, right? The two reactants separate weighed exactly the same as the weight after the reaction. So is this always true? Does the mass of reactants in a chemical reaction always equal the mass of the products?
Yes.
Yes. And what law is it that we know to be true, or as true as scientific laws can ever be? First law of
First law.
thermodynamics,
Yeah,
which
first.
says,
Can't be created or destroyed.
Yes.
Change form.
yes, matter can't be created or destroyed. But that's the law of conservation of matter. First law of thermodynamics is energy can't be created or destroyed, which, being that matter and energy are kind of the same, according
What's
to
the
Einstein.
first law? Matter cannot be,
This
or energy?
Is, no, this is the law
energy.
of conservation of mass.
Oh, wait. Which
But-
one's the...
This, I think you would answer this question better, because the first law of thermodynamics is energy
not
can't be
the
created
first
or
law.
destroyed. No, I would call this the law of conservation of mass, although you could make a good case for the two of them kind of being the same.
Law.
You can convert from mass
Law
to
of
energy.
what?
Conservation of
Law of
mass.
conservation of mass says that matter cannot be created or destroyed, it can change forms. So in a chemical reaction, obviously, It can change from one compound to another compound. But every atom that was in the reactants is going to be in the products, right? Now you might appear to lose mass, right? Say you do baking soda and vinegar. One of the products is a gas, carbon dioxide. It's going to fly away. It appears to weigh less at the end, but if you had captured all the carbon dioxide that had flown away, it would have had the same mass at the end.
Oh, conservation.
Right.
Not
It may
conservatio.
seem to have a bigger volume, like the ammonium dichromate. Remember, it was a tiny orange pile, and then it was like a huge green pile? But it just changed in density, it didn't change in mass, except it gave off some gases too, and if we had captured them, then the mass wouldn't have changed. So the law of conservation of mass is always true for every reaction, except sometimes a nuclear reaction, but you guys don't have to go there, because sometimes they do actually destroy matter and create energy in those. So number 4, how can you separate a mixture? Is separating a mixture a physical or a chemical change, Cameron?
It'd be a physical, right?
Okay, separating a mixture is always a physical change.
Mixture equals physical.
And how would you separate a mixture? We separated a ton of mixtures this year.
By heating it up.
Okay, sometimes you look
Heat
at
it
the
up.
physical properties of the components in the mixture.
Change the temperature. How? Look at the physical properties of components.
Components. Okay, so let's say our two components are iron and sand. How do we separate this mixture?
Could you use a magnet?
Magnet.
Magnet.
You ever get a piece of iron in your eye? Magnet.
Ow.
That would hurt.
It hurts a lot less than the other options. How about red dye 3 and is it 20? I can't remember.
Oh, by water. We used water and watched.
Well, they both dissolve in water, but
But
what
how do
did
you
we
separate
use?
One went, like the red 3 went
Chromatography.
higher.
Oh, my
Oh.
goodness, I can't remember that. So,
Um,
number 4,
graphene.
we got
How about
iron, sand,
sand and salt?
magnet. Why am I writing this down? I'm filming it.
Well, because writing is one more layer of how to memorize stuff. You watch it, you write it, you
3.
think about it, you talk about it.
Chromatography. Wow, that's a big word.
Yeah, sorry.
Chromatography.
We don't know how to spell graphy, so. You guys are remarkably good spellers, by the way. I should always compliment my students on what they're good at. And your lab reports have been above average in spelling and grammar.
Wait, sand and salt. How do you get that?
How do you separate sand from salt?
Water. You put it in water because.
Okay, so solubility,
Okay.
right? Salt will dissolve in water, sand won't dissolve in water. So then you just pour off, filter out the sand. Then if you want to get the salt back, you boil off the water. Well, here, we'll do that one. Salt and water.
Smart. I was going to do that when class was starting.
Oh, that's when we heated up and we watched the water dissolve in the salt. Okay.
So boil off water,
Can we just put heated up?
salt stays behind. Well, and of course you have another option for sand and salt or iron and sand. You can pick out the pieces.
That
bit
takes a
by
while,
bit.
though.
That isn't the smartest choice, but you could do. Let's see. Sand and water would probably, well, how would I separate the sand from the water once I?
Isn't it the same as the salt and water?
No, it's water. Oh, wait, yeah, true.
No.
Strain it.
I didn't
Strain it,
see the
filter.
other one.
Coffee filter, cheap, easy.
Filter.
How about, here's one you don't really need to know. But like if I have rubbing alcohol and water, this is one you'll surely do in college. I hope you don't do it illegally on the side,
Oh,
but you'll do it in the lab in college.
so we're gonna learn how to make drugs.
Alcohol.
Alcohol, my bad.
But you don't want to use rubbing alcohol because that's always poisonous. It's the wrong kind of alcohol. Rotten fruit might. But, anyhow, we're still coming. So how would I separate rubbing alcohol from water, which would not be consumable in any way, just so you know. Okay, well here, you have a boiling point difference. So, remember how something will never go above its boiling point until the phase change is complete?
Yeah.
So you put your mixture of water and alcohol into a flask, and then you bring it to a boil. But the only thing is boiling is the alcohol, because it boils at 70 Celsius, not 100 like water. So at 70 Celsius, you'll see boiling. The temperature will not change again until every bit of the alcohol has boiled away. Then you just catch it, if that's what you want. If you just want to purify the water, you just wait until the temperature begins to rise again, then all the alcohol is gone, and you just have water left in the flask. So, lots of
So
mixtures,
easy.
you can separate easily. Just based on their physical properties. But separating mixture is a physical change. No chemical reaction involved in any of that. Here, we're going way back here. Name some elements. Where would you find a list of elements?
Oh my goodness, periodic table.
Periodic table. If it's on the periodic table, it is an element. Nora, how about a compound? Name a compound.
Sugar.
Sugar.
PbNO3.
Sugar. Salt. What did you say?
PbNO3?
Lead
I
nitrate.
don't know. I
So
was just
lead
going
is a
with it.
2 plus, nitrate is a 1 minus. Lead nitrate.
That's a compound though, right? Because you have to...
Yeah, these are all compounds.
Sugar and salt are?
Yeah,
Yeah.
because you have two different elements.
So you're going to have
Oh.
several questions on this test.
I was just thinking you
Sugar
have to
might
put the two
be
things.
C6,
Okay.
H12.
There we go, that's what I
O6.
was thinking of.
Some
I wasn't thinking of the
sugars-
names.
Some sugars are bigger, like a C12. I named 2 sugars in your
Okay.
test. There's one question that asks you to use sugar for something, and there are 2 different
Sugar.
sugars named somewhere in your test. You can use either of them. But the formula will be somewhere in your test, so go looking for it if you can't remember.
Homogeneous mixtures. Holy cow.
Salt, NaCl is a salt. Magnesium hydroxide is a salt. Lithium chloride is a salt.
Homogeneous
Well, lead nitrate's a
mixtures.
salt too.
I don't remember
So
that.
those are all compounds. How about a homogeneous mixture?
I have no idea. I don't remember those.
Oh, isn't that like an egg?
No, that's
egg.
heterogeneous. An egg is a heterogeneous mixture. Nora? Salt water would be a homogeneous mixture. It's completely mixed. The composition is exactly the same here as here as here as any part of the mixture.
Oh, so it's kind of like a cake. Is that
As long as the cake isn't iced. But a cake might have different compositions because you could get an air pocket in a cake because it has little
Okay.
holes. So maybe a cake isn't perfectly homogeneous.
Okay.
My tea is homogeneous because
What is that?
everything in it is very water soluble, so it'll be thoroughly mixed. So like the sugar will be evenly distributed throughout, the
tea.
caffeine evenly distributed throughout, the tannins evenly distributed throughout.
Tea. Tea. So basically anything that's dissolvable in water?
Yes,
Is that
if something's
homogeneous?
water soluble,
It's
it will form a
homogeneous.
homogeneous
Okay.
solution with water.
Water.
Something like salad dressing is going to be a heterogeneous mixture because you could pick out, I mean, the oil and the water eventually separate at least a little bit. So you can find different pieces of things,
Salad
right?
dressing.
Little flakes of pepper that are different from the
Salad.
mayonnaise part or whatever.
Salad dressing.
How about air? Is air a homogeneous or a heterogeneous mixture?
Air.
Air.
Homogeneous.
Yes, mixtures of gases tend to be very homogeneous because they are moving around so much that they're well mixed and evenly mixed. Air is an important example of a homogeneous mixture. Can you think of another heterogeneous, not thoroughly mixed mixture?
Egg.
An egg is a heterogeneous mixture. It has distinct parts that are clearly visible. How about like cereal and milk? Like your necklace is a heterogeneous mixture.
Awesome.
It's white and black.
Danielle's drink, because it has ice cubes and liquid and has
Daniel's
some
drink.
parts that are different from
Solid
other
flavor.
parts.
Dude, can we put that on the test? What's a heterogeneous mixture?
Well, as long as you
Danielle's
describe it. Usually she has a soda, and that's generally pretty thoroughly mixed. I mean,
Danielle's
the bubbles
Starbucks
might
drink.
mess you up, but
Danielle's Starbucks cup.
I would take, well, if you include the whole cup, then definitely, because the cup part and the liquid part are really different.
Yes.
But they're kind of mixed,
Sorry,
I
I missed
suppose.
it.
So be specific when asked. But I think what I do is I give you a list and you have to name what each thing is.
Okay.
So you can review the little thing on the table. Yes, I just rolled my eyes on camera. Great.
No.
Shut off.
You can just take a copy of mine.
I think
Is mine still running, Justin?
Yes.
Okay.
These three are.
Number 6.
Do we
What
all
are
get a copy?
formation reactions?
Oh,
it
no.
stops by itself.
I can make a
45
copy.
minutes.
Oh, no.
What's a formation
It's still going. I
reaction?
have
When
15
two
minutes.
elements are
It
combined
stops
to
at
make a
25.
Yes. Okay, formation
Stops at
reaction. You
Oh.
start.
Mine's still going. This stops at 30.
Better right.
Mine,
I have 3 hours
Must
and
have
30
stopped at
minutes.
30.
it stopped at 25.
Oh,
But mine's been going for 30.
Can you think
is
of an
this
example?
number
Sorry,
6,
This
right?
is number 6. Can you think of an example of a formation reaction?
What are formation reactions? Ooh, formation element compound. Is that for the formation reaction?
Yes. What would you take 2 or more elements, just like Nora said when you weren't listening, and you form a compound?
Thank you, Nora.
So what are 2 elements that we could form a compound out of?
Like hydrogen and oxygen.
Okay. And this would technically be a combustion reaction because something plus oxygen always burns to be a combustion. So I won't write that one down until, well, later.
Can-
2 elements that form into a compound that you know.
Vinegar, which is like Na.
If we want to form vinegar, that would be a really complex formation reaction with like multiple steps. We'll go with an easy guy.
Carbon dioxide, maybe?
Okay, so if we want to form carbon dioxide, now what's wrong with this?
It's not.
It's not balanced.
There's one massive thing wrong with it that makes it not balanced that doesn't have to do with
It's like
homonuclear
So does that-
diatomics.
Isn't O supposed to have a 2?
Yes, this is a homonuclear diatomic. Make sure when you write chemical equations on the final that everything, anyone give me a list of homonuclear diatomics?
N2,
hydrogen,
H,
I. Right?
no.
Is I one? Yeah, I's
Br,
one.
beryllium.
Bromine.
Is that it? Is that all of them?
And
I think there was like,
And
What are these again? These are.
and
What are they?
Nora said fluorine.
Yeah, all of those guys in the 7th row.
Yeah.
Hydrogen's not in the 7th row.
Well,
There's
no, it
oxygen.
isn't.
It's
Oxygen
the-
isn't
it's the
either.
last.
But the
Oh,
whole
okay, I'll still
7th
write
row
it down.
is a homonuclear diatomic
Because
row.
I'll forget.
So,
CO2.
all of
No,
the
wait, don't
fluorine,
don't
fluorine,
don't
bromine guys.
Just write 7th
We have it
row.
in our book.
Write 7th
Yes,
row.
there's a list in the book, and make sure you
But
don't
I
mess
just,
up
like,
homonuclear diatomic.
that's why I was writing them down. After BR2, what was it? Fluorine.
Fluorine.
And then what else?
Nitrogen.
Study your list of homonuclear diatomics.
Nitrogen?
Yeah.
So that's.
Yeah.
Okay.
So then, okay, so that's an example of a formation reaction. How about a decomposition reaction?
Decomposition.
So why is that one not considered a a combustion.
That's fine.
Well, yeah, you're right. It should be a combustion too.
Oh, so
That's
we-
ugly.
so-
All right, so a
okay, never
formation
mind.
reaction. We'll take our easiest guy here. Now what's wrong with it?
The CL.
Yep, homonuclear diatomic.
Na plus Cl. Cl2N.
So yes, I'll give you definitely 2 combustion.
So the combustion is the
Is there gonna be a 2 at the right there on the
2Na.
at the CL?
No, there's
at
already
the
a
end.
2 there.
But doesn't
There's a 2 right in front of the.
This is a 2.
That's
that's
a 2.
the only 2?
No, there's a 2 in front of the Na2. It's balanced.
2. Oh.
I'd go with the H.
Okay. So we talked about combustion reactions. Anything that burns in the presence of atmospheric oxygen is going to be a combustion reaction. Any combustion reaction I give you on the final is going to be complete combustion. Incomplete combustion forms all of those like carbon monoxide, extra byproducts. But I'm not going to give you, if I say it's combustion, it's complete combustion.
So how do
about
we
a
do
decomposition
decomposition?
reaction? We decompose water here.
Wouldn't it?
When
Go ahead, Karen.
Aren't you just going from H2O down to H and 2?
Yes,
I mean
you
H.
take
No.
a compound and you decompose it into its elements. And of course, there's a million more complexities going on. Or the reverse of this. Ah. But those are,
There we go.
so if I ask you a question where I say a formation reaction occurs between this, and then I ask you a question about it, you're gonna have to write the equation before you can do the math.
Oh no.
Right. So, I have a note to tell you about one particular combustion.
Okay, write this down.
So I don't know why I have this note, but I do, so we'll just talk about it. So this is methane, CH4, and it, well, combusts. And what are the, what are almost always, but apparently not completely always, the products of a combustion reaction?
CO2 and H2O.
Right. CO2 and H2O. Because in a combustion, you can combust just carbon, like, because the coal is pretty much just carbon, graphite, just carbon. But normally you would be burning a hydrocarbon, like a fuel, methane, propane, butane, like in your lighter. This is methane. If you burn it in the presence of oxygen, then you get those standard complete combustion things. So complete combustion is always going to produce 2 standard products, carbon dioxide and water. They're always going to be at high temperature, so even if your fuel is a liquid, which methane is almost always a gas at normal temperatures, but a lot of, like butane is liquid inside your lighter, right? Propane is liquid inside your propane tank. But whatever it is, everybody else is going to be a gas, because obviously combustion is hot.
Are we gonna have to make sure we do this on the test? Make sure it's with the little symbols thing.
The phases.
Yes, include phases. Speaking of, I wonder where this question is. What are the phases of matter, which is a different meaning than the word phase, meaning solid, you know, like, what are the phases of matter? There are 4, but you probably only learned 3 of them.
Where is that question?
I don't know if it's even on here, but I know
Oh.
it's on the final. I happen to remember that now that we mentioned phase. The word phase threw people off because they're so
What
used to me
are
saying include the phase.
The
But if I say what are the
phases
phases of matter?
of matter. Oh, it's just like Like gas, liquid, aqueous.
Aqueous is a phase, as in during a chemical equation you include the phase. But aqueous isn't a phase of matter. Gas, liquid, solid. And there's a fourth one. It's actually the most common phase of matter in the universe and the least common on Earth, probably.
Gravity.
What's the sun? Anyone know? Only one person actually got that last year. But I don't mark off if you don't get the fourth one, but it's plasma.
Plasma.
It's superheated gas.
So is it just P? Right?
So solid, liquid, gas, and plasma.
What's the thing for plasma? The P? Like, what's the...
No, these aren't phases that you would include here.
Oh.
These are just, like,
Oh.
this is like a middle school science question. The phases of matter are solid, liquid, gas, and
I don't
plasma.
even know plasma. What's one phase?
But yes, that has nothing to do with, although there's some overlap, the phases that you would
On
write in a
final.
chemical equation.
Boom. Pat.
Well,
Getting that one
let's
right.
see.
I got one right so far.
But in combustion, you know, pretty much you're dealing with gases. How do homogeneous catalysts work to decrease activation energy and also heterogeneous? Who wants to take on this
Homogeneous
one?
catalyst work to decrease activation energy.
I don't know.
Okay, so when you have energy diagram, thank
No,
goodness
no.
I can think of the word.
Can't even see the
Okay,
board.
so you have energy on the y-axis, and you have like this might be like time, kind of, as the reaction goes to completion along the x-axis. Okay, so when you're looking at an energy diagram, where would delta H be?
Delta H will be in the on the energy thing right there. Yeah, right there.
Okay, so delta H is from the energy of the reactant to the energy of the product. Okay? And if it's negative, then
Wait,
what
is the
kind of-
delta H the going up or the one going over? Like, is it the dotted line or the arrow?
It's the arrow.
Oh, it's the arrow.
Delta H is the difference in energy between the reactant and the product, and that's called enthalpy. Remember enthalpy?
Oh, yeah.
Enthalpy. If enthalpy is negative, which this enthalpy is negative, then what kind of reaction is it? Well, I'll just put a negative sign. What kind of reaction do you have if delta H is negative? Endothermic or exothermic?
Wait, if it's negative?
This is exothermic.
What was the question?
Okay,
Is
if
it
delta H is
ring?
negative, then energy was more here, some got lost, given off as heat, and it's now lower than it was to begin with. Okay, exothermic, gave off heat, has a lower energy state at the end than it did at the beginning. And of course, if it's positive, then you have an endothermic reaction. And that means it took in heat from its surroundings, so it will feel cold, takes in heat, and ends up, you know, at a higher energy state than where it started. So this here is an endothermic energy diagram. It ends up with a delta H that's positive. Where's the activation energy?
Up, like the bump.
The bump.
The
Okay, so
The hump.
this is activation energy. And what does a catalyst do to activation energy?
maybe.
What was the question? Sorry, I was writing.
To the activation energy.
What does a catalyst do, Cameron?
No pressure.
No pressure. It's seriously, like, this is 90 minutes of a whole year of chemistry, so no pressure. It's hard to remember everything.
I really don't remember.
Anyone know what a catalyst does?
It
Catalyst. What is it? You go, because
I thought it made it higher, but I'm guessing it makes it lower.
A catalyst reduces activation energy.
catalyst reduces. So how do homogeneous
So there are two
catalysts
kinds
work?
of catalysts. I ask what first? Homogeneous catalyst. So what do you know about a homogeneous catalyst? How about phase? What is it? The same phase or a different phase?
It's the same phase.
As at least one reactant. A homogeneous catalyst is the same phase as at least one reactant. And does it get used up and then reformed, or does it just act on its own without participating in the reaction?
It participates with the
It
reaction.
does. A homogeneous catalyst okay, so two things. Same phase as one reactant at least. And participates in reaction and is reformed by the end. So you never run out of it. It's always present during the reaction because it's like a three-step reaction where it
In what?
is a reactant,
Participates.
then it
Participates
lowers
in what?
activation energy by
In the
being a
reaction.
reactant, but then
Oh.
it's reformed. So you end up with the same amount of the catalyst at the end as you had at the beginning. But it did get consumed and reformed.
Reaction.
Kind of like a cyclical thing, consumed and reformed. Heterogeneous. Okay, a heterogeneous catalyst is going to be a different phase than the reactants. And it does not participate in the reaction. So, how does it lower activation energy if it does not participate in the reaction? So let's say I'm a heterogeneous catalyst. I am,
Are we doing homogeneous first?
No, we're doing.
we already did
homogeneous.
homogeneous,
okay.
now we changed color.
Oh, I thought we were doing the.
Oh, we already
Question.
did it. If I'm a heterogeneous catalyst, let's say I have an electrostatic charge, right?
Yeah, I know.
So I'm going to
But we're on
attract
This one.
um,
We're done with that one.
some
Let's answer that one.
of the reactants to myself, right? So I'm going to increase the concentration of the reactants in the area where I am. Increasing concentration increases reaction rate, right? So I'm like a little ball of concentration. I attract them and then they react with each other. They don't react with me, I just attract them so they end up closer to each other. Okay, like a matchmaker.
Okay.
Do I have to sing the song? Yeah. Good. Horrible high school musical memories. Fiddler on the Roof, if you need time to relax after finals. Heterogeneous catalyst is like a matchmaker. It brings the reactants closer to each other, causing them to have a regional increase in concentration, which increases the reaction rate, lowering the activation energy. So, bless you.
Bless you.
Is the camera still running?
Yes.
Yes.
Okay. Number 8, make sure you know how to find molar masses and review stoichiometry. So that's chapter 10. Well, I know you all know how to find a molar mass, right? Let's say, just real quick, what's the molar mass of sodium hydroxide?
Where's the periodic table?
Right.
I'll add it up. 23 plus. Oh, 16 plus
101.
1.01.
It's not good.
40.01.
Okay,
So 40.0.
But I know oxygen is 16, hydrogen is
And
1.
then sodium is 23.0.
Alright, so 40.0. And this one doesn't cause any rounding, and we only have significance in the tenths place, so it's going to be 40.0.
Not
And what's my unit?
AMU.
Okay, for one
It's gram.
molecule.
Oh.
It's gram, right? Gram.
If I'm asking the mass of one
Gram.
molecule of
It's
sodium
gram.
hydroxide,
It's
it would be
definitely gram.
AMU. per
But it's gram.
molecule. But for
It's
molar
gram.
mass, it's going to be 40.0 grams per mole of sodium hydroxide. This is what you're going to use math-wise, grams per mole. Right? With it, you can probably find density if you have a certain mass. You can find, if you have moles, you can find grams, so you can measure that out. And what is a mole exactly, just so we all remember?
Mole.
A really small number.
A huge number.
Yeah.
Huge number. 6.02
Yeah.
times 10 to the 23rd of
Come on.
something. Just like a dozen is 12 of something, a mole is that many of something.
Jeez.
So this is like, I think they said, if you had a mole of soda cans, it would cover the earth to 100 miles deep or something.
Oh, wow.
Yeah, a mole is such a big number. Like you can, it would take a computer like 1,000,000 years to count to a mole if it counted 10,000 a second.
Dang.
Right, a mole is like a vastly, unbelievably humongous number.
Why do we work with it?
But you should probably know the mole number, 6.02 times 10 to the 23rd, is Avogadro's number, and you should probably
What is it?
memorize it. Avogadro's number.
6. What?
6.02
6.02
Times 10 to the 23rd.
times 10 to the 23rd.
23rd is.
Avogadro's number.
How do you spell that?
I don't
Yeah.
think I asked you that. It's a guy's
Is-
name, so it's capital A-V-O
A-V-O
G-A-D-R-O.
G-A-D-A
R-O.
R-O.
It's the Italian scientist.
Avogadro.
Yeah, him.
Okay.
Dro's formula. Or
And of course, celebrate Mole Day on October 23rd.
oh, is that mole day?
Mole Day,
Oh,
10/23.
nifty.
Yeah.
That's the day before my birthday.
Aw.
So I get cake both days.
Yeah, that's right. Mole-shaped cakes, please. So number 9. Here's another one of those questions that you don't want to get to the final and not know because it's so easy and you'll kick yourself a lot. How many electrons, protons, and neutrons are in one nuclei of uranium-238? So Nora, tell us how to do it.
Like 92 electrons. And
So how did you find that out?
Well, because it's right here.
Okay, look right at your periodic table. This is why I don't want you not to get this right. So you look right at your periodic table. You use the bottom number for molar mass calculation, but the top number tells you what?
The electrons and protons.
Yes. As long as there's no charge, then it'll have an equal number of electrons and protons.
Oh, oh.
So this number comes right from the periodic table,
So.
the top number.
And then
And how do you find out how many neutrons?
You minus them out of the. Yeah.
Okay.
from
Okay,
Right, right,
so
right.
238 minus 92.
92
142.
electrons. 92. So you take 238 minus 92.
Because
Okay.
what's in
These are
the
all in there.
nucleus?
I know. It was in the middle of the year. I don't remember.
No, they were in the quarterly test.
I haven't
You
taken
haven't
the
done it
quarterly
yet.
tests.
You didn't take them yet?
What
I've been waiting for
is-
this.
Yes, do this
First.
first, and the quarterly test will go faster.
Yeah.
What
I already did them all.
is?
I haven't done it.
What does the 238 mean?
Oh,
That was brilliant.
I coughed with this hand. I coughed with this hand.
That's why I was like, oh
I
no.
was like, oh, you really don't want me to cough.
Y'all are missing out on what's going behind you. So, what does the 238
You're missing out,
mean?
Austin.
Are we on number 10?
You got
Still
that?
on number 9. What does
Oops.
238 mean? Just so we're all real clear on how to
238
do
is
this.
the. Oh crap.
That's molar mass.
No,
No.
it's the
It's the
Ion
number of
something.
things in the nucleus. Okay, this 238 is number of things in the nucleus. What's in the nucleus? Two stuffs. Which two stuffs?
Oh, the electrons and
No.
Protons and
These are
neutrons.
Protons and
There's
neutrons
no
are in the
nucleus.
nucleus. Okay, they're held together by
I have
weak
no
and strong
clue.
nuclear forces, which actually deduct a little bit of mass, which is really cool.
Neutron.
And you should read about that someday. But anyhow, if you know that this is all that's in the nucleus, and you know this number of things is in the nucleus, and you know there are 92 protons, then you can easily figure out how many other things there are, and since every other thing is a neutron, there are 146 of them. Okay?
So the neutrons and proteins are in the nucleus.
Proteins.
Protons.
Protons.
My bad.
Proteins are huge compared to an atom. Because they're like a bajillion atoms all mushed together.
Protons.
Bound together, I should say, I guess.
In that way.
So number 10, what wavelengths are visible light?
Oh. This
About.
chapter.
Oh.
Yeah,
Oh my gosh.
Oh.
this reappears in physics, but it's not hard, don't worry.
It has to do with Roy G. Biv, right?
Roy G. Biv. So
Which is-
every light from red to
Red,
violet is
yellow,
visible. Do you know what
green,
the...
Indigo.
Violet.
Right. No, Roy G. Biv, and no.
Clean hair.
The only thing you need to know
No.
is... Yeah, there they go. The only thing you need to know is...
Stop, guys. You're embarrassing me.
It's all Justin.
No, it isn't. It's
It
not
is
me.
too.
It's Cameron.
Okay, visible light ranges from about 700 nanometers to about 400 nanometers. Okay, and the other thing you want to know on the final is the 700 end is red and the 400 end is violet. Okay, if you know that much, you're going to be
No
fine.
memory space. My memory card.
Allison will now delete videos or
I already
survive.
did.
Oh, that
Well,
is.
you can just take home a copy of mine.
I didn't bring anything.
I
Don't
can
worry about it.
email
No
you
worries.
one.
Yeah.
Can you email that?
Probably. Yeah. If I put
So
my
long.
SD card in, and then I can plug it into my computer and then email it.
But how long will that take?
Not long.
I've tried to email videos
Crap.
to Sam. He said it again.
Good thing that's right when you sat down. Woo!
And
Nope.
is mine still going?
Don't delete it.
Shoot.
Did you
You just
delete
delete
it?
it.
I pressed save, but it didn't save it.
Oh well, my
I
video
can
is
send
still
you.
rolling.
I can send you mine.
Crap, man.
It's still recording, amazingly enough. It's just not yours. So
Okay. That sucks.
Okay, you might have.
please
I'll send you
note while we
I'll
are
send
in
you the whole
damage
thing.
control here,
Crap,
these
man.
two equations.
I hope I
right
can
here-
watch it. What are those two equations?
E equals HF, where H is Planck's constant, which is on your test.
What is it?
At the very
Planck's
beginning,
constant?
Planck's constant, H. I give you the value of H on your test. It's at the beginning of the test.
That's an HF.
Frequency.
I know it looks like
Planck's
Oh, okay.
constant
H.
times frequency.
So
Energy is equal to H
But what-
times frequency.
What formula is that?
E equals HF. That just is.
But there's not a name. It's not a name of a formula.
You'll use it again in physics. I don't
E
know.
equals H.
What,
Everyone just
what
called
do
it
we
equals
use it for?
H.
There's energy.
Well,
Yeah.
if you know frequency, you can find energy. If you know energy, you can find frequency, because Planck's constant never changes.
And then what's the other
C
one?
is the speed of light.
Oh, that's
active-
frequency.
Yes.
Alright,
Wait.
did we answer the first part?
Of 10?
Wait, that's not.
Is that what that is right there?
Yes.
That's the wrong formula.
The visible spectrum is from 700
C over
nanometers to
wavelength.
400 nanometers of wavelength.
Okay.
So it's like the
And-
second question.
Isn't that the wrong formula? Isn't it C over wavelength? Isn't F equals C over wavelength? Not wavelength equals C over F.
Well, if I rearranged it, it would be this.
So it's exactly the same.
It's exactly the same. It's just an algebra thing. I mean, these two are the same formula.
It doesn't matter.
You just you solve for whatever you're solving for. And what's C again?
C is.
Color. Okay.
No.
Opposite.
C is the speed of light,
Oh.
which I think I put on your test.
Yeah, we wrote that.
3.0 times 10 to the 8 meter per second. Or if I wanted it in a different unit.
That's
I
the
could have
speed of. So
That's the
C.
speed of light. C is this.
C equals
So
speed
it'll
of
always
light.
equal that?
Yes, it's actually 2.998 times 10 to
But you're
the
just gonna make us do the 3 point.
Yeah, 3.0 is fine. Two significant figures will do for us. Not for like if you were shooting something into space or.
But how we do that
if
every
you
day.
pair,
Crap! Why did I erase that? Dang it!
M for S.
what?
And
It flipped though because I flipped it over.
Meters per second.
And I
Got it.
saved them.
Velocity is
Nice.
always meter per second. Speed is velocity.
Ah.
Meter per second. Not mass. Meter per second.
Mine's the last.
So, when do excited atoms emit their signature color of light? So do y'all remember when I took those powdered salts and I burned them and they gave off light, like a firework? When do excited atoms emit their signature color of light? Yeah. Okay, electrons get excited. They go out to higher energy levels, higher orbitals, right? When you heat up or excite them with electricity or whatever, then they go out to a higher orbital. When they come back to ground state, to decrease in energy, they emit energy. They give off energy so they can go back down. Right? Just like a little kid has to burn off energy before it can sleep. An electron has to give off
Uh-oh.
energy to return to ground state.
Cameron,
Processing.
something died.
Is mine still running?
Yes.
No, it just paused.
Mine's a work.
Press
That's
the
used to.
shutter button to begin recording.
There you go.
Oh.
Okay, so
That's
weird.
must go off. It goes off
So,
every couple.
excited atoms emit their signature color of light
15
when
minutes or
they are
something.
returning to ground state.
Minutes.
When they're de-exciting, returning to ground state.
Okay.
They have to give off energy to go down in energy levels.
So
Wait,
that's for
what
the
question are we
question
on?
number
That's number 11.
Okay.
Oh wait, what was 10?
10
Did we
is,
get that?
Yeah,
10 is the 7.
this.
Yeah.
Oh, that's that. Okay.
But make sure you know these
What's
two
11?
equations also.
when they're
And I'm pretty
returning
sure I
to
put the speed of light, and I know I put Planck's constant on the final.
Can we just repeat number 11 one more time? When they what? When they...
When excited atoms, well, their electrons are excited, they're in a higher energy state. When they want to return to ground state, they have to give off energy to decrease in energy. So they emit light to give off energy. Light is energy,
What was that?
right? Light is energy. They give off light to
When they're
reduce their
returning to
energy and
ground
go back
state.
to ground
That's
state.
it. Oh, when they're returning.
All right. How do covalent bonds form?
Oh.
Number 12. How do covalent bonds form?
Gosh darn.
Like, you know where you...
Covalent bonds.
Remember.
Ion change?
No.
Round.
They're not ionic.
It's one... Isn't it... Yeah, covalent.
Amazing.
Isn't when one's like bigger than the other and they grab some kind of pool?
Remember.
Okay, so tell me something that is covalent. Covalent compound?
Oh.
What's covalent? Anything.
Hydrogen. H2O.
It
I was trying to
is.
think of what it was called.
Okay. So,
Really?
Water.
so we have oxygen. Remember if you do its Lewis structure? It has 1, 2, 3, 4, 5, 6,
You
right?
do it.
And then
Do it.
you
Maybe.
bring in the
at me, bro.
hydrogens. Hydrogens each have one electron, right?
Yeah.
Right. So, how do they form bonds?
By sharing.
Sharing electrons. Covalent
Oh, how do covalent bonds form?
equals sharing electrons.
Covalent equals sharing electrons.
How do ionic things form bonds?
By taking electrons.
Right. Ionic compounds literally, so let's say,
Steal
salt.
electrons.
Yeah.
Ha!
I like my take.
No,
So-
steal sounds better.
So sodium has, what, 1 electron. Chlorine has 7,
Oh, such a dork.
right? So chlorine just steals the electron. And then why are they attracted to each other? If there's no electron sharing, what holds them together? Why do they have a bond?
Because. Yeah.
Because
Yeah.
it's an
I
electrostatic
was gonna say
attraction.
it, but then she wrote.
Positive
That's
attract
why.
negatives. Okay, this has a literal negative charge and a literal positive charge, and that makes them attracted to each other. So, an electrostatic attraction is an ionic bond. It's not a real bond. There are no electrons shared. Oh my goodness, we're having a problem.
It's gonna be a really interesting video.
You know, it always is. I have